Now you may notice something kind of interesting here, because slope is defined as change in y over change in x. But this also looks like a right triangle. So, and therefore, the slope is sort of like the tangent. So you can combine the properties of the tangent, and so by finding the slope of line DE, you basically found the tangent of some triangle formed over here. And then you can take the distance of AF or FB or whatever, and then since it's equal to that distance, you can find the position of point C, and then you could just flip it over to find point E over there. So great, now you know what the left and right flanks are, but there's still one part remaining. Since this is a formation, it's not just going to have one unit in it. They're going to organize them in some formation like this, with the lines and these squares forming here. Now first of all, let's just pretend that these are aligned to the x and y axes. Then it's pretty easy to find where to do this. And let's just pretend this distance is 1, and then we could make it more complicated later on. Then, if you're going to number the units like 1, 2, 3, 4, 5, 6, etc., then the y position would be approximately the unit number divided by the number of units in a row. Might be plus or minus 1, I don't care right now. And then the position on the x-axis would be the remainder of dividing the unit number by the width of the formation. And these might sound kind of like weird functions, but they're actually pretty standard in programming. So yeah. But now we have to rotate it, because the x and y axes aren't necessarily going to be oriented that way. But that's still pretty easy, right? Because let's just say your formation's like that, and you've got your right triangle there. So you just so let's just say this is cosine and this is the sine. So since you've kind of found the position relative to here and here, so the x-axis would be the cosine and the y-axis would be the negative sine, I think, something like that. Now I'd like to note one thing. When we are numbering the units, there's some algorithms to optimize which units go where, to minimize the distance they have to travel, but I haven't exactly figured out how that works, so since I don't know how it works, there's no way I'll be able to explain it here, but I just wanted to let you know that such things existed. So now you've found the starting position and the ending position, but now the units have to move there. So if you just tell them to go in some straight line to the final position, it's not going to look very good. And so first of all, let's say I'm just going to draw based on flanks instead of the boxes, since you could find the individual position since you could find the units' positions from the flanks. So first of all, let's just pretend that there's some ideal flank positions as the time increases. So the time increases, the ideal flank positions go along there. And then you tell all the units to try to go in the ideal position in the flanks like that. Well, that's going to work okay, except that it's going to be very slow because you're going to be giving new commands to all the units every frame, and that's going to make the game lag, especially with lots of units on screen. And another way you can do it would be to find the intersection point, so that if the unit travels at a faster speed to the formation and then a slower speed when they're at the formation. So let's just say we've got some individual over here, and ideally they would move along a straight line like that. They're going to move a faster speed to get onto the line, and then a slower speed once they're on the line. And even though that only gives 2 commands and only has to be calculated once, it's still a pretty slow calculation. So, after hours of observing Medieval 2 Total War, I noticed they use this really cool optimization. So, here's our starting flank place and the ending flank place. What Medieval 2 Total War does is it defines this flank in between, that's slightly in front of the starting position, and they tell everyone to arrive over here at the same time, where the slowest speed is so that every unit can travel at a reasonable speed. And then they just walk from over here to here. And that's going to work really well. So now we know how to find where the unit's going to go and how it's going to get there. Or not quite. Because one thing that's almost inevitably going to happen while the units are moving is that they're going to collide. Now, so typically the best way to do this, now let's break this up into 2 parts, collision detection and collision response. Typically the best way to work with these things is to treat them as circles. And then you see that if the sum of the radii is, if the sum of the radii is greater than the distance between them, then there's a collision. But remember, there's also the distance optimization I explained earlier, and that's pretty important to use, and that speeds it up quite a bit. But still, when there's thousands of when there's 1,000 units on screen, that's still going to be awfully slow, because there's like 1,000 units checking for like 1,000 factorial collisions, which is comparable to 1,000 squared, or something like that. So you still have to reduce the number of collisions that you check for. So a good way to do that is to break up the world map into a bunch of grids, and the units don't even have to be nicely placed within the grids. But then you can just check collisions for the square that the unit's on and the surrounding squares. So this unit here wouldn't have to check with collisions here, but they'd have to check with this one and this one. So that's quite an improvement.